Okay, so in this video we will examine gravitation and dark matter. As before, you should see the previous videos before you start with this one. You have to understand things like particles, matter, what is how it's working, what is also electromagnetics and things like this is necessary to understand the following. So we see that the universe is filled with free daons, and they are clearly dominating. So we will start with just have a look at the free daons and what this can give. So free daons are filling up the whole universe. Interaction between the free daons are also important. You have that the interaction between free daons, the force between the free daons in medium is zero, but there is one specificity, and that is the size of the free daons. If the free daons are smaller, their interaction will be stronger, and so this will tend. I mean, if you see the interaction between different sizes of daons, you will have the tendency that the bigger free daons will become smaller, and the smaller free daons will become bigger. So after some time, you will have free daons with about the same size. If you don't have some certain fields or effects of something, free daons should have about the same size. At least locally, you might have variation to big distances, but locally it should be about the same. Now, we will now make an hypothesis to explain how the universe is working and also gravity. We need to make the following hypothesis, that is that our universe is a big sphere, and around this sphere there is an empty void, not necessarily empty, but whatever it contains, this void around our universe, do not interact with our universe. So this is a stepping scenario. You go to something enormously much bigger. We do not understand infinities, but I mean, we cannot even imagine the infinity, but we can imagine that the universe is a sphere, and around this sphere we have some empty voids, which probably goes to infinity, but okay, let us stop there. Dark energy is the energy supposed to make that the universe expands. Now, such an expansion cannot be anything else but some force pulling the universe apart, and this can only happen in an interface between our university and the external parts. Since the free daons has no force within themselves, inside the universe you have no force to expand it. The only possibility is in an interface with something else or nothing else. Okay, so if you look to this, you see this formula here. This shows interaction zones between free daons, and you have that you have 12 interaction zones of attraction and 12 interaction zones of expansion. And in free daons, usually these are equilibrated, so that the force, the total force is zero, or medium force is zero. If you go to the surface of our universe, in this case, you have surface daons, which are interacting between them, but you have no interaction zone versus the external part of the universe, because there is nothing, which means that you get more expansion than contraction of these daons in the surface of the universe, which lead these daons to expand. If they expand, then also its neighbors below and around will expand, and you get the force of expansion of the sphere. So all this is quite simple, and you can calculate this. I mean, you get 6 zones of expansion. The three zones of attraction becomes expansion, so you get total of 6 expansion zones, more than you should have if it was inside the universe. So, and this you can express in the following way: you get an acceleration of expansion, which can be expressed like this. Well, okay, then we add another hypothesis, quite logical, to say that the number of daons within our universe is constant. I mean, that seems quite logical. We don't create daons like that. It's just a specific number of daons within our universe, and it doesn't change. So in this case, we can then express the number of daons within our universe in the following way here. Quite simple. It's just the volume of the universe divided by the volume of the daons, multiplied by filling factor in volume in this case. And then we can do the same thing for the surface daons. So you take the surface and you divide with the number of daon surfaces comparable. Multiply this time with filling factor, which is flat surface interaction between equally sized spheres. Okay, so now we can combine this equation that we have already seen together, and we obtain that surface action, let's say, of the universe versus the external part is quite simply 36 times c squared divided by the radius of the universe. Here we have to be a bit careful because the radius of the universe is not too well defined in the case of the universe being extremely big, because the influence from the internal part of the universe comes with a delay to the external part. So this should be corrected for this delayed expansion, which is not easy to do. So this we will leave for people who has programs to do these things. It has to be three-dimensional with delayed potential, etc. This is not so easy. So I will leave this to somebody else. But you have here the equation that you can use to look into this. Okay. We will have a look at Hubble parameters. Hubble parameter is just the speed of expansion of a sphere divided by its radius. So you can take the whole universe, or you can take just a small sphere within the universe, and the result will be the same. If you now use the hypothesis that the number of daons within the universe is constant, then you have that the expansion of the universe must be followed by the expansion of the daons. So the daon expand with the same velocity as the universe. And so you obtain a nice formula here showing the velocity of expansion of the daons, or the universe, as you like, and in this way. So from this we can say what happens then if we change the size of the daons. What happens to the mass? Let's say, for instance, of an electron. What happens? Will the mass change of the electron if you in the expansion of the universe? That is a very important question, to see the parameters variation or various constants, things like this, with the expansion of the universe. First we calculate the mass of the electron. We do that numerically with the help of simulation programs like EP, for instance. And so you do that, or you just take the number of daons within an electron. You multiply with the order which are keeping the shells together, and again you multiply again with the order to have which part of this daons associated with the electron are really following the electron in its movement to space, because only some daons are following the electron and some are left behind. So we have to again multiply with the order, and you make then the sum, or better the integral, over these shells of the electron, and you obtain this formula here. There is no analytical expression, since in the central part of the electron you have a reduction of the radius of reference, which gives some problems. So you can make this numerically and you obtain this value here. So, okay, you have seen already most of this. I mean, the distance between one shell to the other is square root of 8 divided by 3 times the radius of the free daon, or the daon. Okay. So, after some analysis of this with the simulation program, we will change the size of the free daons, and we keep the mass of the daon constant. That should not vary. And we obtain a law which shows that the mass of the electron is proportional to the size of the free daon. So this is a very important conclusion. So then you can then say that since the free daon is modifying its size with the expansion of the universe, you can directly use the same thing for the universe size instead of the free daons. The correct use is to use the free daons as indicating for the change of mass. If you use the universe, you have to, it's a very small correction, because the sum of the daons are introduced into the mass of the electron, for instance, or masses in general. Have an increase or diminish the mass of any particles due to the size of the universe. So this changes slightly the number of free daons. So it's better to use free daons in ratio free daons instead of the radius of the universe, but the difference is quite small. Now, what does it mean? It means that when the universe is in expansion, the mass is growing, as we see in this formula. Now, if the mass is growing, then you have to have a flux of free daons going towards all masses in a way to increase the mass. You need free daons going into the masses. So in an expanding universe, you will have an attraction of free daons versus the masses. Then you have to, when we took a look at the calculation of the electron mass, you find there is we multiply, we take the number of daons, we multiply with order, which are to keep your shells together, and then we again multiply with the order for the daons which are following the electron in its movement. But this last order, which is daons following or not following the electron, these are also a mass, and a very big mass in fact, because if you look to this mass with taking away one O, then you have one order, then you have that the radius doesn't disappear like that. I mean, you have an R, you multiply this constant with a radius, and this becomes bigger and bigger and bigger when you go away. So it's proportional to R, this mass. And this becomes extremely big. In fact, the limit will be the universe itself. It's really, really enormous. That's to show just that radial equilibrium around an electron or positron, whatever, is always there. I mean, you cannot just take it away. Like, for instance, you have an electromagnetic interaction. Now, if you have the electron, you have also some positive charge somewhere. So after some time, then the electric potentials disappear, or electric fields disappear. But the equilibrium, radial equilibrium of an electron must always be there to keep it together, otherwise it would explode. Which means that it has to be replaced, this electromagnetic interaction will have to be replaced, and there is only one possibility, and that is the size of the free daons. So when you come close to a charge, you have the free daon size going down slightly to create a radial equilibrium around the electron if there is no field. Okay, so this becomes a very important mass around each charge, and this is then accumulating onto the electron when the universe is in expansion. So now we can look at this. We see we take a sphere around some mass, and we can calculate how many free downs pass through the surface of this sphere versus the inside. And you have this is equation here, quite simple. It's just with the sphere, you multiply this with the speed, and you have that this is a number of downs going in. We will make also another equation here that shows that which defines how many downs or free downs we need inside the mass to keep it incoherent with the external free down size. The free down increase, the mass increase, and you can calculate this also inside the mass. If you do this, you obtain some nice equations. You can see, for instance, that the electron's reference radius, area infinite, is also growing. This is growing with the factor, the ratio between free downs now and free downs in the future, multiplied by so the power of 4/3. This comes from the calculation of mass of the electron, which we showed earlier. So you have the cube of the ratio between free downs and the reference radius of the electron and the free downs on the cube. And if you want this to grow with the expansion of the universe or the size of the free downs, then this ratio has to be to the power of 4 to 3. Okay. Now you can put all this together, and you obtain a velocity of the free down flux going towards an electron, for instance, or a mass, or whichever mass in this equation here. And as you see here, this is dependence becomes 1/r, which means that this velocity of free downs moving towards all masses is always there to the limit of the universe. It's always a movement from free downs towards the masses, and the speed can be calculated in this way. If you look for this on the surface of the Earth, for instance, you obtain that is 1.35 meter per second. So this is not neglectable, because here Earth is a small mass. I mean, you get to a black hole, and then the mass of this radial flux is growing to high values. So now we come to the explanation of Newtonian gravitation. We have made some preparation now here. So first we should say that if you have a flux of free downs, let's say around an electron, as usual, we have seen with magnetism that the flux like this doesn't give any supplementary effect. In fact, it's the same thing as the inertial velocity. You can also say, and what about the velocity of the flux? Maybe that has something to do with some extra force, but also that is not possible, because you have if you have a velocity of, you can change the velocity of an electron, for instance, within the flux, and you can make this velocity bigger than the flux of free downs around it. And in this case, you should have some effect giving the force in the opposite sense. And we know that this is not the case, so this is also excluded. So there is one more possibility, which of course is the correct one. And this is that when you have a mass with some position, let's say let's take a sphere just to make it simple, but you can make any form in principle. Let's say a sphere, then you have a radial movement of the free downs going versus this mass, which means that the radius around the sphere is reduced, so that you have less and less place for the free downs, let's say. This effect makes that the free downs are compressed, and you have a modified size of the free downs getting smaller and smaller the closer you come to the mass in question. This, since we have the velocity, we can calculate the compression, and this is quite simple. You have these equations here showing that you have an azimuthal compression in this sense, and you have also a radial compression also in the radial sense. But the compression in the azimuthal sense is stronger, factor 2 times stronger, pushing on each other like this, which reduces the size of the free downs. At the same time, you have a compression also in radial sense, but it's half the value of the compression in azimuthal sense. So this means that the downs become smaller in the azimuthal sense than in the radial sense. And this leads to not to a compression, but an expansion in the radial sense. So the effect is 2 times azimuthal and one minus 1 in corresponding 1 in the radial sense. So you get a difference in the sign of the compression. If you take the total compression of the down, you obtain, you see this formula here, and you obtain that radial compression is 1 divided by 6 times the speed of the free downs in the flux divided by c, the speed of light. And this you can now introduce the free down speed, flux speed, as we presented earlier, and you obtain the final equation like that. Now, so what can we do with this? You have a compression, so it means that you have a difference in size. When you come closer to the mass, you have smaller downs, and this of course have some effect on the force. And so you calculate this again on an electron. We see what you calculate the effect on the surface of the electron, how the force depends on the variation of the size of the free downs. If you do this, I will not show you too much of this, because it's, as usual, it's difficult to show the mathematics in the videos. It's really difficult to explain it. But I will show you this formula quickly here without too much explanation. And you compare this with Isaac Newton's classical gravitational formula, and you obtain the G factor. You can calculate it immediately. This is quite straightforward. Here we should explain something else, and this is that the G factor, or the big G of Newton, is not very well known. I mean, it's 3 digits maybe. It's a big error bar, but it's 3 digits or something. And then inside of this formula you have the Hubble constant. The Hubble is not well known at all. It's between 68 to 72 kilometers second parsec, so whatever, like to mention this. So this is a big error bar. You have not even more, have 2 digits with a big error bar. So we make something. We take the G factor, factor G, which is known to 3 digits, much better than the Hubble constant, and we calculate the Hubble constant using this formula. And what you obtain from this is, you see here, the Hubble constant becomes 72.2 kilometers per second and megaparsec. And this corresponds more or less to the experiment, or the measurement calculations of this Hubble constant in the local area around our sun. So this is, since the Hubble constant is modified with time, I mean the speed and radius of the universe is changing. So this is the Hubble constant at this moment in time, close to our galaxy. Okay, so this now is an explanation for the Newtonian gravitation. I think it's quite nice. It gives the correct result, more or less, and this is very nice. Okay, we should mention that the photon and the neutrino are not sources of gravitation, because their downs just modify slightly their internal equilibrium to make up for any gravitational force, external force acting on them. So they are not sources of gravitation. but they are influenced by the gravitation because they have a radial equilibrium or an equilibrium, internal equilibrium. So if you put in a gravitational field, they will feel it and they will move towards the gravitation just as any other particles. But they have another characteristic also, both of them. That is that they are following the free downs. So if you look to some, take the photon passing the sun, for instance, is deviated 2 times more than a normal particle, also a neutrino, the same thing. This is due to the fact that they are following the flux of free downs. If you bend, you get the curvature of the photon, let's say, or the neutrino, then they have no centrifugal force keeping them in the correct straightforward direction. But there are no transverse force. So they are bent 2 times more than a particle, which a particle has, since it's rotating and moving in a certain direction. You have forces keeping it in position, so then it's bent. They have a transverse force, which is going against the gravitation. So photon and neutrino don't have this. Their reaction is completely different. So they are bent 2 times more than what should be expected. You should notice here also that since neutrino has a specific geometry, the photon has a spherical geometry, so it's easy to calculate. The torus of the neutrino is different, it's perpendicular to the speed, and so this is more delicate to calculate, and you get some correction probably. I will not try to calculate this, it's quite difficult. So I didn't try to calculate it, but could probably be made by some clever scientist. In any case, it's different and should give a different gravitational force. Okay, so we move on and we now go to examining what is a black hole. When the mass of a star becomes bigger and bigger, or the mass of whatever lump, you get the mass becomes bigger and bigger. And of course, at the end, you will reach the light speed of the flux of free downs towards the mass can reach the light speed, and if it reaches the light speed, then you cannot get out from this mass. So this is what you can define as a black hole. And if you look to the compression of the free downs, you can see that even if the flux speed comes to c, the speed of light, you don't compress the free down to 0. It's the maximum compression you can obtain is 5 divided by 6 times the farther away free downs the size. So you are limited in that. You should also understand, as we examined the proton, that the proton is a particle which is extremely stable, and so you cannot compress the matter below this limit. So the density of the proton together with the electron, you have to have both for charge neutrality reasons, and they cannot be compressed below the density of the proton. And maybe you can compress a bit, but not very much. So you have a limit about 10 to the power of 18 kilo per meter cube, which is the density approximately of the proton. And a black hole or whatever other mass cannot compress below this limit. So if you then you can then put in this in the equations here, and you obtain that the mass of a black hole is proportional to its radius. So the bigger the radius, the bigger the mass of the black hole. Okay, so now you can put this then into the equation of gravity, and you find that the force of gravitation on the surface of a black hole becomes weaker when the black hole becomes bigger. Okay, so this is just the inverse of the radius. The bigger the radius, the weaker the gravitational field of a black hole. So this is specific. Okay, you can then also calculate, if you want, the density of a black hole in general, and you've put this inside the limit just to look for the smallest possible black hole, which should correspond more or less also to the maximum size of a neutron star. You get a radius of 10 kilometers about, which correspond more or less to 2 solar masses. So a black hole cannot be smaller than 2 solar masses, and a neutron star cannot be bigger than 2 solar masses. Okay. If you examine this, you see also that you have a frame dragging, that is that the space around it, the free round flux, goes into the masses, so you have a radial frame dragging, and of course you have also an azimuthal frame dragging, that is in the accretion disk around the black hole or some masses, neutron star for instance. If the particles in the accretion disk exceeds the light speed, which could happen, then the whole mass of free daons will move around with the accretion disk, and you have a rotating frame. That's called azimuthal frame dragging. Okay, so we will take continuous black hole jets. If you have a black hole, sometimes you have some jets coming out from the poles, and you wonder what is this about. And this, from the DAON theory, you should expect that this, when you have an interaction with another big mass, and whatever, then the accumulation of mass onto the black hole will be too much to reorder quickly the surface construction, let's say, of the internal protons and neutrons. So you have that the mass will start to slide towards the poles faster and faster, what you're filling up on the accretion disk on the equator, and then you have the mass going to the poles. And if you have sufficiently big mass to accumulate onto the black hole, then this could result in a clash at the poles, and you have jets coming out from both poles in opposite directions. As before, when you have this on the surface of a black hole, then you have that the size of the free daons now are 5 divided by 6 of the free daons further away. And this means that you have a variation of the energy within these jets, which seems to be that they are further away due to the redshift. We will examine redshift a bit later on, but you have a tendency to say these jets from the black hole has a tendency to be understood as something further away, because you have a strong redshift that seems they are further away than they are in reality. So this is a problem. Okay, so we will now go over to dark matter. Dark matter, already the phenomena of dark matter is when you see a rotating galaxy and you try to calculate the velocity of rotation of the galaxy. This can be measured due to the redshift, and you see the velocities at the various radius. If you calculate that in a classical manner, you find that the rotation is much too fast farther away from the galaxy, and it's normal maybe close to the galaxy, or you can put it like so, but then it should go down with the classical laws with the radius, and it doesn't. It just go faster, too fast in a bigger radius, and this is a problem, and the only explanation for this is that it has to be some hidden mass or something like that inside the galaxy, which makes that the speed of rotation is bigger than it should be, and so this is the phenomena of dark matter. Of course, what is hidden here of the dark matter, in fact, is what we discussed earlier, is the hidden mass around charges, which do not follow the charge in space, but the mass is there. So there are big masses around black holes, for instance. They have a hidden mass. You can calculate the mass of the black hole when it's moving around to some close neighbors. But you have a hidden mass which is go much further out around the black hole. In fact, it goes to infinity. And this is very complicated to make a precise calculation of this external mass, because we don't have experimental measures of parameters of importance, which is the surface conditions on the we have to know surface conditions to decide the interaction strengths, and this is not well known. There are some approximation, some values you can extract, but there are very big error bars, so this is not any very high precision. But in fact, you can make some calculation since we know the the extra mass added to an electron. We can use this to put this on the surface of a mass in general. If you make some estimation, you soon realize that you don't really have to occupy yourself with planets or stars or things like that, because they give a very small contribution. The main contribution comes from black holes, especially the central black holes. So galaxies can be very strong and contribute very big mass to the galaxy. Sometimes even in the size of the galaxy itself. I mean, it's very strong. Then you have also that, for instance, neutron stars and black holes, planetary or star black holes, they can contribute if their number is sufficiently high. So you have to see if inside the galaxy you have a high number of neutron stars and black holes, then you have to sum this all up, and then this could contribute in an important way also. But essentially this is the central black hole that is very important. So in this I've made some equations. I will not even show them because you will not understand it. You have a table where you have some values that can be extracted from literature, but as I told you, this is very uncertain values, some estimations more or less, and it's not very well known. I make also some estimation in the text, but okay. So you see I'm reading from this book, which the DAON Theory. You can find on Google. You just write the DAON Theory book, for instance, and you obtain this thing here. And you have some more details in instruction, etc. So if you look to the dark matter business, you get that the dark matter around a black hole, for instance, varies as 1/4 the radius. So, which means that this influence is continue to going further and further away, so that you get the correct force to make this rotation of galaxies if you have a strong contribution from dark matter, that is black holes and neutron stars, if there are many, etc. So when you come far away from a galaxy, then the 1/r component will dominate completely, and the 1/r the normal gravity, let's say, will be neglectable when it's a certain distance away. So you have also that when you have this 1/r, you have to go to radius until you have some other galaxy has the same force as you at the same distance. And so this is then limits the influence of the dark matter to some local sphere around each galaxy. But this, if you go for instance to the surface of the universe, and you have to sum up all these masses to have the correct value at far off. Okay, so with this we will stop this video, and the next video will be the last one. This will treat then the characteristic of our universe, some specificities about this, many subsections treating various things. So to the next video.